Hi everyone, this is Jesse here from SkyCiv, and today I just wanted to talk about bearing capacity, what it is, and how we can design for it. So first of all, the bearing capacity of a soil is its ability to resist shear failure under vertical loads, which can come from structures like strip footings, pad footings, crane outriggers, basically any structure on the surface of our soil applying a vertical force could develop a bearing failure, and we need to be able to design to ensure that we can resist this by running these bearing capacity checks. So if I just take a screenshot of that, we can draw on top of it. And what a bearing failure is going to look like is we're going to have a shear failure that develops, and it looks something like this. As this shear failure develops, we have the soil start to move, and we're going to get some heave in the soil to either side of a foundation, and the foundation is going to start to sink because it can't resist this load, whatever load that is. So there are a few different types of bearing failure. The one I've just drawn is the general bearing failure, which would occur for dense or hard soils. But we can also have a local shear failure or a punching shear failure. With these methods, the failure plane wouldn't fully develop like this. And for example, for punching shear, we just get this guy going kind of straight down and shearing quite locally. And with the punching shear failure mechanism, we wouldn't get heave like this. We might not get much disturbance at all, just because we're failing so locally, we're not pushing the soil all the way to here. A few methods have been developed around the general bearing capacity failure. And those are what we're going to talk about, which are covered by this tool. So with that failure mechanism that I've shown, we could do a kind of analytical calculation and look at the shear strength of the soil. That's been done, and it turns out that results in a very conservative design, which is not reflective of real world conditions. So in the laboratory, a few tests have been done, and models have been developed by a few people in the past. So it started off with Tazagi and his bearing capacity calculation, which had a few less factors than these other methods in future would also consider. But at the end of the day, all these methods are estimation methods based on laboratory results, so it could be useful to compare a few of these different methods when we're doing our bearing capacity check. A really useful thing as well is to be able to run a sensitivity analysis. So we might, if we just use all these default inputs, we might want to run a sensitivity analysis to see how the width of our foundation, for example, is going to affect our design. So if we had a minimum width of 1 going to a maximum width of 3, we can run this design just for these default inputs and see how this is going to affect our design bearing capacity, and how it's going to change for our different methods. So when we run this and we scroll down through all our calculations for our specific inputs, we're also going to get a sensitivity analysis graph, which shows that as we increase our foundation width, it turns out our design bearing capacity is also going to increase. And we can also see the relation between our different methods. So for the inputs given, Hansen appears to give the most conservative results. But comparing these different methods, we might want to take a average, a median, or we could just choose to use the most conservative result. That's up to the engineer to decide. But basically, this is a tool allowing us to see how these different methods are going to give us different design bearing capacities for these specific inputs. So let's take a look at what separates these different analysis methods and what's involved in the calculations. So with a bearing capacity check, we're of course going to use our design loads. This is kind of standard specific. In design soil parameters, again, so design standard specific. But for all our methods, we're going to use our moments and vertical force to get effective dimensions, which in this case are just the same as our actual dimensions. But if we had some moment, we would start to reduce the length of the footing that we use and the width of the footing that we use in our design. When we have a water table, we're also going to get an effective unit weight to account for the effects of the water table. In this case, I think we don't have the water table impacting our design, so our unit weight is just the soil unit weight above the water table. And we're going to have other calculations like the effective surcharge, which is just considering the load adjacent to our foundation, which in this case is 0, but I could add some load here, and that's kind of what this would look like. And when I go back to this report, we can see that we'll just then start our bearing capacity calculations. These are all very similar. So we're going to have shape factors, depth factors, inclination factors. In this case, it's 1 because there's no incline load. And for Tazagi, there won't ever be inclination factors because it's not something that's considered in that method. And for all our methods, we get slightly different bearing capacity factors, which is going to result in our slightly different results. So all these results in general have this same formulation of the bearing capacity calculation. They're just going to have slightly different factors, and some methods will have more factors than others. But at the end of it, we're going to calculate our design, our ultimate bearing capacity based on 3 main components: the ultimate bearing capacity related to cohesion, ultimate bearing capacity related to the overburden pressure, that Q that I just showed when we vary this, and the ultimate bearing capacity related to the soil weight. So these 3 components are shown here. We can see that actually in this design example I've shown, only 1 component is actually giving us strength back. That's because our cohesion is 0, so our cohesion term goes to 0. Our overburden is 0, so this term goes to 0. And we're going to have our 1 term giving us our bearing capacity in this design example. And then finally, we can, depending on the design method used, get our design bearing capacity. And this design bearing capacity is just going to consider all the reductions that we use, be it material reductions on our soil or a partial reduction factor on our bearing capacity. That's going to give us our design bearing capacity, whereas the ultimate bearing capacity value, this doesn't consider any safety factors, and no matter what standard we use, when we compare our ultimate bearing capacity, we're going to get the same number because we haven't used any reduction factors for safety yet. And with this design bearing capacity, we can compare this to our design pressure to get our utilization value. And from this design example with just these values that I've put in, we can see we have a utilization of 66%. And so for this calculation, our bearing capacity is passing. We also have some extra checks just to make sure that the structure is not sliding and it's not overturning. And those are included in this section of the report. So that's an introduction to bearing capacity, what the design looks like, and how we can use the quick design bearing capacity calculator design for these different inputs, generate sensitivity graphs, and get bearing capacity results quite easily using this tool. If you have any questions about this video, you can leave a message in the chat. Otherwise, I'd recommend you to look at the other videos in this series or just play around with the calculator yourself and get a feel for what it does and how you can use it in your own real-world designs. Thank you for watching. Bye.